The objective of this experiment are first to characterize the physical and chemical properties of slag generated from pyrometallurgical processes. Second, to evaluate the potential utilization and environmental implication of slag as recyclable byproducts. Slag is a byproduct formed during high temperature pyrometallurgical processes such as iron making and copper smelting. It's formed when calcium oxide reacts to impurities like silicon and alumina to produce molten silicate phases. Due to density difference, slag flow about metal and can be separated easily. Typical slag contain calcium oxide, silica, iron oxide and alumina. Today, slag widely reused in construction material, road base, ceramic production and metallurgical application.
For methodology, the experiment began with sample preparation by crushing the slag using a conventional hammer. Next, physical observation was conducted to analyze the color, texture and fracture behavior. A water absorption test was then carried out using a vacuum desiccator. After that, the more hardness test was performed using a diamond tip tool. Finally, mechanical strength analysis was conducted using the 3-point bending test. The slag sample was manually crushed using a conventional hammer to produce smaller particles. This process allowed easy observation and analysis of the material. During crushing, the slag broke into angular and irregular fragments, indicating the material is highly brittle.
So, guys, ini slag. So kita akan buat inspection first. Dari segi dia punya tekstur adalah kasar-kasar lah. And then lepas tu dia ada, nampaklah ada porous semua. Dari segi luar dia macam dalam dia kelabu, and then luar-luar dia macam warna hitam sikit lah. So itulah untuk dari segi visual inspection untuk slag ni.
The slag appear dark grey to charcoal in color. When crushed, it produced a fine and gritty powder texture. The material was highly brittle and could be easily broken into angular fragments. This behavior indicates high silica content and rapid cooling during slag formations.
The vacuum process was carried out using a vacuum desiccator. This process removes the trapped air from the pores of the slag sample. As a result, water can enter the pores more effectively, producing a more accurate water absorption result.
The water absorption test was conducted to determine the porosity of the slag. The calculated water absorption value is 17.21%, as this indicates the slag is moderately porous due to the presence of many internal pores.
Boleh faham? So this is a lab. So mula-mula kita kena dapatkan picture dan microstructure.
The most hardness test was performed using a diamond tip tool. However, the result was inconclusive. This is because the slag surface was uneven and highly porous. The diamond tip entered the pores instead of producing a consistent scratch on the surface. Do the SRD analysis for the fourth lab. So first, we import the file first. Okay, import the file. So the next step is to search and match. Don't forget to choose the crystallography open database and search and match. So now let's find what pixels they are there. First we will start with quartz. And next one is kaolinite. And the next one is magnetite. So once we have completed this first quartz, and then we have to create a DB view. Okay, then based on the pattern we can create a pattern chart. Okay, last but not least, we will print preview. Okay, so we'll get this and also the pie chart. Yeah, save.
Based on the SRD quantitative analysis, the slag sample consists of three main phases. The dominant phase is archemanite at 50.4%, followed by quartz at 21.8% and magnetite at 19.9%. This composition indicates that the slag is rich in calcium silicate with presence of silica and residual iron oxide. The SRD graph shows several sharp peaks together with a broad background. The sharp peaks confirm the presence of crystalline phases such as archemanite, quartz, and magnetite. The broad background indicates the glassy presence of an amorphous glass or glassy phase formed due to rapid cooling. This shows that the slag contains both crystalline and amorphous structures.
Mechanical strength analysis. The mechanical strength analysis was carried out using the 3-point bending test. The slag-based ceramic achieved a flexural strength of 55.53 MPa. In comparison, the commercial ceramic recorded only 24.65 MPa. This result shows that the slag-based ceramic has significantly higher mechanical strength. Although the raw slag is brittle and highly porous, the presence of strong crystalline phases such as archemanite improve the strength and performance of the ceramic material. Discussion. Physically, the slag show high brittleness and high porosity, as indicated by its high water absorption value of 23.24% and its irregular fracture behavior after crushing. SRD analysis confirmed the presence of crystalline phases such as archemanite, quartz, and magnetite together with an amorphous glassy phase. For mechanical properties, the slag-based ceramic achieved a flexural strength of 57.53 MPa, which is higher than commercial ceramic. This shows that although the raw slag is brittle and porous, it can develop high strength when processed into ceramic material. In terms of recycling potential, the slag is suitable for construction material, road-based, and ceramic applications, while also helping to reduce industrial waste and support sustainable development. Conclusion. In conclusion, this experiment successfully characterized the slag sample and evaluate its recycling potential. The slag was found to be highly brittle and highly porous, with a water absorption value of 23.24%. However, the slag-based ceramic demonstrate high mechanical strength at 57.53 MPa. SRD analysis confirmed the presence of stable crystalline phases such as acamanite, quartz, and magnetite. Overall, slag is not simply waste, but a valuable secondary resource with strong industrial potential.